Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to unpack Kirchoff's circuit laws. Alright, so Kirchoff's first law, as we saw, was intimately related to a fundamental physical principle, which was the conservation of charge. That is, the conservation of charge applied to a circuit gives you Kirchoff's first law, which says that the current in, or the sum of the currents into a junction are equal to the sum of the currents out of it. What goes in must come out. As it turns out, Kirchoff's second law is also related to a conservation law, and we've already sort of stumbled upon it in our discussion of potential and potential difference, which is the conservation of energy, right? So fundamentally, the same kind of reason that the potential gained in the EMF, so any energy per unit charge given to the charges in the battery, has to be exactly equal to the potential lost, or the energy per unit charge lost in the resistor, can be applied to any loop in a circuit. Okay, so this is known as the loop rule rather than the junction rule. And Kirchoff's second law says that in any closed loop around a circuit, the total sum of the potential gains is equal to the sum of the potential drops. In our metaphor, where potential is kind of like height, if you go on a hike up and down hills and valleys and you come back to the same spot that you were originally in, then the total height you went up has to equal the total height you went down. That's exactly what this says. It says the sum of anything going up must equal the sum of anything coming back down. So the sum of the EMFs around a loop are equal to the sum of the potential differences down around the loop. Another way of saying that that the IB will write is just the sum of all of the potential differences, including both gains and losses, equals 0. I prefer to sort of think of it this way, where like your ups are equal to your downs, but it's really up to you, and both of them can be applied here. So if we apply Kirchoff's second law to our original simple circuit, it just says the sum of the EMFs, in this case just the EMF, is equal to the sum of delta V, and the sum of delta V here is just the potential difference across the resistor, and therefore EMF minus delta VR, which is written kind of like this, is then equal to 0 volts, and the EMF is equal to delta VR. Now, Kirchoff's second law can be used to analyze a whole bunch more different kinds of circuits and to give us a lot more information about those circuits. Consider the following circuit with two identical resistors wired in what is called series. Recall that series means one right after another, sort of end to end. Well, if this is our circuit now, so now we have two resistors, how are the EMF and then delta V1 and delta V2 related? Well, if we apply Kirchoff's second law, then the EMF in this loop, right? So we go around the loop once, that EMF has to be equal to the potential drop across the first resistor and across the second resistor. And if they're identical resistors, then the EMF is equal to delta V1 plus delta V2, and delta V1 equals delta V2 because the resistors are identical, right? They're going to be treated the same, sort of by the physical world. And therefore, the EMF is equal to 2 times the potential difference across each of the individual resistors. So for example, if the EMF is 10 volts, then the potential difference across this resistor would be 5 volts, and the potential difference across this resistor would also be 5 volts. We can represent that graphically right here, just as we would before, by sort of going around the circuit. The potential at 1 can be set to 0. You gain a certain amount in EMF, and then you lose half that potential difference across the first resistor and half that potential difference across the second resistor.